Today we will talk about similarity indexing, more specifically about metric indexing of multimedia or of any unstructured objects, uh, where we are concerned with the issue of scalability, not anymore the modeling issues. And as was announced in the previous lecture, we will deal with different types of metric indexes or so-called metric access methods. I have split the methods into 4 categories. First one is based on simple distant matrices, also called pivot tables. Then the largest category is hierarchical structures, tree-based structures, because there is a huge tradition from database indexing structures from the past. So these are also following this database trend. Then there are some also hashed indexes, and there are some also hybrid indexes that combine more principles into new designs. We'll also discuss the measures of performance when evaluating these different structures and comparing which one is better than the other one. Of course, we must take into account context, the problem, database, the distribution of the database. Many factors come into account when comparing structures. But from the performance point of view, we can restrict to optimize or to pick the right or design structure based on best performance in terms of distance computations needed to answer queries or to index data. Then the traditional aspect of I/O costs or disk access costs, which is related to secondary memory access. Then there are internal costs that are specific to the particular algorithms and data structures that are hidden in the particular method. And of course, the ultimate real-time costs, meaning the wall clock time, that basically is the most important in terms of the final usage, but is not so important in the design time, where we play with the structures, not with complete softwares, and we don't have a fair platform to compare methods based on the real time. Okay, we start with motivation. We already know that effective search means search that corresponds to users' expectations, so that's the quality of the search. And in terms of similarity search, it's about the quality of the similarity model. And now we will discuss the efficiency issue. So this is purely the database aspect of fast search. So we do not care about the models anymore. We of course accept them in the metric space formalism. So we have some black box similarity model, and now we have to index the data under this model to be efficiently searchable. As we have introduced in the introduction lecture, the indexing principles are based on so-called lower bounding mechanism that allows to or is a general mechanism for computing lower bound distances that are cheaper to compute than the original distances as a part of the similarity model, that are also more expensive. So we are trading expensive distance for its cheap lower bound. Of course, the quality of the lower bound is dependent on many factors as well. The metric space model then is a concrete model how to generally compute these lower bounds, because without any other information than just the black box distance function and black box descriptors, we don't have any clue how to construct lower bounds. So with metric space model, we have a mechanism how to generally construct lower bounds, and the principle is, of course, the metric postulates and also some pre-selected objects from the database called pivots that serve as kind of anchors to which distances are pre-computed, and these are used as a so-called coordinate system. So these are somehow special objects that are fixed for the indexing purposes. We can interpret the lower bounding as partitioning the space. We can view dual. We can view this duality. Of course, we have the lower bounds. This is what we have exactly, but we can also transform these lower bounds into the geometry analogy, and this means for us for the indexing case, partitioning of the data space, and this partitioning then serves as a way how to index data and how to prune partitions in the space that do not need to be searched when querying. Okay, the area of database indexing that deals with this similarity search under metric space is called metric indexing, or generally metric access methods. I will repeat the basic assumption we already had in the introduction lecture, and that's the general lower bounding principle that assumes that we can construct a lower bound distance to our distance that is given in the similarity model, that is basically the black box. We don't see inside the structure, or we do not expect to see the structure, because we work on the black box basis to be as general as possible. And we have this situation that is the typical situation by querying. We have one particular object from the database, X. We have a particular query object Q. It's query by example. We have one example that's Q, and we have a range. So we have a range query, and it's to the object Q. We have radius R, and we are searching for all objects in the database that fall into this ball. Apparently, in this example, this object X is outside of the ball, but we don't want to determine this fact by computing this distance, because computing distance from Q to X is the way how to confirm the object is or is not in the ball. But it's too expensive, because there is not just one object X, but we have many of objects. The database of millions of objects, for example, so we have millions of X everywhere here. And instead of computing these direct distances Q to X, we would like to use another distance that is cheaper to compute and serves the same purpose. So instead of excluding these objects from search because this distance is too large when compared to R, it's outside of the ball, it's enough to have another distance that is just a lower bound, not the exact distance Qx, but some lower bound. But the lower bound is large as possible to approximate the original distance from below, of course. And in this particular case, it will serve the same purpose. It will filter out the objects X from search, because the lower bound is larger than the radius R, so the true distance must be even larger or the same, but for the fraction of the cost, because this is easier to compute and this is hard to compute. And that's basically the principle of indexing. And of course, the success of this method is only as good as good we have ways how to construct these lower bounds. Generally, we need as tight lower bound as possible, meaning largest as possible, because of course they are by definition smaller than the original distance. That's why they are called lower bounds. but within this constraint we need as large lower bound as possible. The other extreme is zero lower bound, which is basically useless because every zero falls inside the ball, so nothing could be filtered out. And when something is not filtered out by lower bound, then the direct distance must be computed and verified whether the object is outside or inside. And basically this is what happens in sequential scan, which is the baseline method, just comparing as many distances as many objects are in the database. So for 1 million objects, there must be 1 million computations of this distance performed. So we want to avoid the full scan, computing millions of distances. Okay, so in this general case, we don't know how to compute lower bound because we know nothing. So to know something, we introduce the problem to be in metric space. So in addition to the black box distance and black box descriptor, we now have also 4 metric postulates, 4 axioms. That is reflexivity, non-negativity, symmetry, and triangle inequality. And we know something more about the space because all of these must be satisfied. And they are also, at the same time that they are mathematical properties, they are also somehow natural to modeling similarity, because similarities must follow some cognitive properties of human mind, because similarity is something related to human judgment. So reflexivity says just trivial thing that two objects are zero distance, so they are maximally similar only in case, or just in case, they are the same. So if the objects are really the same objects, measured by bit representations, for example, also their similarity or distance must be absolute. So distance is zero or similarity is maximum. The complement to this is non-negativity, that says the complement. So if something is different from something else, also again by some bit representation or content representation, then it must be positively distant. So it cannot be completely the same. So both of these assumptions are kind of natural to similarity. And the third property is symmetry. And here we stated that it doesn't matter from which direction we measure the distance, or we view this two objects as similar. If we first look at x and then at y, or the other way, first at y and second to x, it doesn't matter and it's the same. Again, this could be viewed as not problematic. Of course, all of these properties could be questioned by psychological theories of measuring similarity or modeling similarity, but for our purposes we need some compromise, some trade-off between the restrictions, the constraints, as these four, and the freedom of modeling of similarity, because we need some information about the space to be indexable. The fourth property is the most problematic and most non-intuitive, but still it's valid if we admit that similarity must be transitive, because we force the similarity to or the distance to comply with the triangle inequality, saying that for any three objects, if we have one object somehow distant to the other object and the other object to some third object, then the cumulative distance must be larger than the direct distance between x and z. That means basically, when translated into the terminology of similarity, that it cannot happen that if two objects x and y are very similar and other two objects y, the same y as here, y and z are also very similar, that then it cannot happen that object x and z are not similar. This is basically what triangle inequality says. So there is some kind of transitivity in the similarity. And again, it's a valid assumption in many cases, especially for global descriptors. This is quite valid argument. It is not working with partial similarities, because then the triangle inequality is often violated. But we are now working with some trade-off model that allows indexing in metric space model. So we assume all of these properties as reasonable for similarity, and it's also useful for indexing. I just remember all of these discussions we are now doing are just for the sake of scalability. So we want to speed up the search in the database. If we don't have the problem with speed, for example, we have very small database, then we basically don't need to index anything and just use the sequential search, and it's okay. But once the database grows beyond some limits, then this becomes an issue. So that's what we are now discussing. Okay, so in specific model as the metric space model, we have the previous example concrete. We have the query ball as in the previous picture, with object Q and radius R. We have the object X, which is representative from the database. We have millions of these objects X, and this is some new object P that is pivot, and this is some special object pre-selected from the database, because we don't have any other repository where to take the object. And based on this object P and the distances computed between P and X and P and Q, we can use these two distances to compute lower bound distance between Q and X. So if we subtract these two distances in absolute value, we get this green distance that basically is a lower bound of distance QX. And in this particular case, we can see that it's good lower bound distance, because the object X, we see it's outside of the query ball, and also the lower bound distance is larger than the radius R. So based on comparing these two, we can safely confirm that object X is outside of the query ball. Now, how this was computed? I said it must be cheap distance. So this is expensive and this is cheap. So how it is cheap? It seems that it's not cheap, because instead of one distance, we must compute two distances, this one and this one. But these distances, there are also many of them, because these are millions of objects, are pre-computed in the indexing phase. So this is why we are talking about indexing, because exactly these distances, either directly these or some induced ones based on the indexing structure, of course, are pre-computed and stored in the index. There is not many of the pivot objects. It could be just this one, or a few, or definitely a static number. So this is number of distances that is proportional to the size of the database. So this is the size of the database is linear with the number of course is a parameter, the size of the database. Then the number of these distances is again linear with this size. The other distance QP cannot be pre-computed, so it must be computed at the moment of query, which is bad, because we won't process the query fast. But because the object P is just one, or there are a few pivots, we are not computing millions of these distances every query, but just a few, or just one. So yes, at the query time, there is some extra distance computation needed, this one, but then we can construct all of these lower bounds for free or not for free, just for fetching the pre-computed distance from the data from the index and using this distance QP. And then we can or we expect to filter majority of object X out of the search, because every reasonable query should return as positive results, so those really falling into the ball, only a few out of millions. So otherwise it doesn't make sense. So just imagine you have Google, and Google indexes billions of web pages, and it only gives you 10 pages as a result. So this is the assumption. The query result is just a few answers, and the irrelevant objects, the non-relevant object X, that's a huge multitude. So this is the basic mechanism, and now we will detail how this information is basically stored in different types of indexes, and how it's used for querying. Also, before we proceed to the particular indexes, we can more discuss or more elaborate on the usage of the lower bounds, because the lower bound, that's basically everything, and we can use the lower bound, as in the previous example, individually for every individual object from the database. That means instead of computing 1 million distances QX, so we have 1 million lower bounds QX and filtering. Or we can have some sophisticated data structure that also organizes the data in some clusters or in some regions, or in something that creates a structure on the database. And for example, in this case, we have a subset of objects that are wrapped inside a ball because the centroid object is considered as pivot P, though it's basically one of these objects O, but it's pronounced as a pivot for the situation. And then we have a covering radius that basically ensures that every object within this ball falls inside this ball. And then the distance from Q to this ball, basically again a distance QP, and instead of Px as here we have the radius, so we can compute the same lower bound as here, but now it's for the whole region of objects. So in this case we could filter out from search a whole region, so it's not necessarily to be done individually like here 1 million times checking for this lower bound, but in hierarchical structures there are some regions, and we could quickly filter out groups of objects. So this is the second case, and the third case is more complicated. It also introduces upper bound into play, and partitioning of the space by something that could be called generalized hyperplane partitioning, because we are in metric spaces, so all of these pictures are just Euclidean illustrations, but we are in metric spaces, so we must be careful about definitions. So in the hyperplane partitioning we have two pivots, P1, P2, and then the rest of the database is distributed between these two pivots very, very easily. All of the object is assigned to that pivot that is closer. So all of these objects are closer to P1, all of these objects are closer to P2, and all objects that are on this line, just a hypothetical line or hypothetical hyperplane, are exactly in the middle. So they are the same distance to P1 and P2. And if we have the query again, then we must decide whether the query spans or overlaps this half space or this half space or both, like in this case, and we can easily detect this property by checking out whether some hypothetical object within this ball must be, or all hypothetical points in this ball must be in just one half space or the other half space or in both. So there are just three cases, and we can I will talk about this later, but we will need upper bound to any object of this ball, which is basically distance from P2 to Q plus the most distant object from Q, so it's the R, and the lower bound, which is basically the same but minus R. So we already had this. It's like here. Okay. So these are three principles that could be used to filter out the region under different circumstances within the metric indexes, and all of these, of course, have the same objective to provide efficient, fast search. So now, if we have an index and the index is composed of some aggregated lower bounds, that means we have some regions. As I said here, we don't have just individual lower bounds like in this case, but we could have a region, a sphere region, ball region, like here. So then we are in we have some elementary geometry to be matched with So we have the query ball. I have two cases for L1 metric and Euclidean metric. Basically, it's the same data and the same distances, or not same distances, same radii, but different metric. So, and we have two different cases. So in Euclidean case, we see that this gray ball is a region in an index. So there are some objects inside that basically are described by this ball. The distribution of them is described by this ball, and this is query. And basically, this is the basic situation in index. When we are querying, we have the query ball, and we want to check whether the query ball overlaps some data ball, and so the data ball must be inspected. So in this case, it must be inspected because there is non-zero overlap, and we find out by very simple inequation if the distance between OI and Q is smaller than the sum of these two radii, then they overlap and there must be search. Otherwise, they could be this region could be filtered out from search because they are not overlapping, which is the case of the L1 metric, because in this case the distance between the Q and OI is larger than the sum of the radii. So this is the ball-shaped case of matching a query. If we have the hyperplane-based case, then we must work with the lower bounds and upper bounds, and then we basically watch the query ball as hypothetically full of answers, and we have to determine if the answers can only be in one of the half spaces or in the other or in both, as I said. And we could do this with a simple trick, and the trick says if the close, because it's important to realize how these half spaces are defined. They are defined that they consist only of points that are closer to OI than to OJ. So the same we can ask when determining the overlap. So if the closest object from this ball, query ball, to OI, so the lower bound distance to this query ball, is larger than the largest objects from OJ in the query ball again, then the whole query ball must be outside of this half space, as in this case. So the lower bound here to the ball, to any point in the ball, lower bound, is larger than upper bound to any point in this ball from the other side, from OJ. So then there cannot be any point here that is closer to OI than OJ, just by metric properties. And then in this case, if this is a region of an index, it could be filtered out from search, and search continues just in this one. And recursively, of course, it applies. It could be also generalized to multiple pivots. We can have not only two, but multiple, arbitrary. And then it's very similar, but we must do this checking for every point, for every pair of pivots. So this is just basically incremental process. And this because all of these are just illustrations in Euclidean space, so we must strictly work just with the inequalities that basically are based on the metric space axioms that are again inequalities or equalities, and work with the predicates, not with geometry. So the geometry is just illustration, but what's important is the inequalities. And in the inequality says, so what I said, if the upper bound, if the lower bound is larger than this upper bound, then this could be filtered out. So if this is lower bound to OI, this is OIQ minus R, and if this is larger than the upper bound, which is OJ to Q plus R, then we can filter out region OI from search. And of course we also check it from the other side. So if the lower bound of OJ to Q, which is this one, is larger than the upper bound of OI, which is this one, it could be filtered from search, but it's not true in this case, because this is just very small lower bound. Okay, so this is filtering of metric regions for the purpose of queries. We have always a ball of a query, and either ball of a region or some half spaces or some subspaces of data. And now how this materializes in the metric indexes. So as I said, there are various structural designs of these indexes, starting from very simple ones. There are maybe it's a strong word to call them indexes. It's just matrices, distance matrices, somehow stored or in memory. Then there are hierarchical indexes, trees basically. Then there are hashed indexes. There are also the hybrid indexes that combine many of these together, and there are also index-free methods that do not need to index first something and then query, that combine the indexing into within the search. So they're kind of caches or more flexible structures. Okay, so metric indexing, and basically they have all the same objective. The objective is to create index that allows searching for similar data, so processing similarity queries, by limiting the number of regions of the whole database to just candidate classes that are guaranteed to be relevant to the query, and everything else is guaranteed to be non-relevant to the query. So this is basically the principle of speeding up, filtering something from search and searching only in a fraction of the database. This is basically general indexing concept. This is not specific to metric indexing. This is valid for any index in any database indexing. So this, you can see this principle in other techniques. Okay, so the first class is pivot tables or metrics methods, and it was also the one of the oldest. And it basically the first one, first method or first index that has the acronym AESA, approximating and eliminating search algorithm, is basically algorithm, is not called data structure, because the data structure is just metrics. And this metrics that is used by the AESA is basically, or this method is kind of extreme. So it was first and extreme. And because the extremality of this method was that every data object within the database was also regarded as a pivot. So there was as many pivots as objects. So every object was a pivot. So there was a square matrix expected. So we had a square space complexity of this method, because we really have every object, distance of all objects to all other objects. And because this is a huge matrix, of course, it's quadratic, then the price for this was empirical constant time for nearest neighbor search, because that was a trade-off. Extremely expensive construction of the index that was really rewarded by the really fast searching. But this was of course not scalable. So there was later a linear version of this algorithm introduced that didn't expect the same number of pivots as objects in the database, but there were only some constant number of pivots assumed, of course selected out of the objects. So we got a matrix that was not quadratic with the size of the database, but only linear. That's why it's linear. So we have some k that is constant. And now it is also good method to visualize the problem of the geometrization of the lower bounds. Imagine this example. We have metric space. In this case, it's Euclidean space, but it's generally metric space. And we have two pivots, P1 and P2. And all of these circles just denote distances by some steps from P1 and also P2. So we have 1, 2, 3, 4, 5, 6, and so on, and 1, 2, 3, 4, 5, 6, and so on from P2. And in the pivot tables, what is in the linear version, what is done is that all of these data points that are basically black box descriptors, so we don't know nothing about the structure of the points, of the objects, we transform them into vectors, k-dimensional vectors in the pivot space. In this example, we have just two pivots, so we have two-dimensional space. And the space is constructed really easily. We construct the coordinates as the distances to the pivots. So in the first coordinate, first dimension, we have first dimension with the first pivot, second with the second, and so on. So with the first pivot, we have distance to P1. So for example, this object 08 has coordinates 1, 2, and half from P1. So first dimension it's 2.5, and second dimension is 1, 2, 3, 4, 5 and a half. So 2.5 and 5.5, and here is the 08. And everything else we map the same. Also the query point could be mapped the same. So like from this point and this point. So we have there. And the only weird thing is that the Euclidean ball here changed to square. And this is because we need to provide contractive mapping. So this mapping, this projection from the metric space into the pivot space is done under the L max distance. So we do not measure these points by Euclidean distance anymore, because basically we don't know that's Euclidean distance, because this is general metric space. But here it's not metric space. Here it's vector space with k dimensions and Lmax distance. And based on Lmax distance, all of the mutual distances between the objects here are the same or lower as between the same objects here when using the Lmax distance. Lmax distance means we are measuring the distances only orthogonally to the system, so and taking the largest one. So if 08 and 07 is this or this, and this one is larger, then the distance is basically this one. So and you can easily verify that all distances here are the same or smaller here. But this is also the source of error, because these distances are not preserved exactly. They are approximate, but they are guaranteed to be lower bounds, and now we are again in the lower bound concept. That will introduce some error. So, for example, in the original space, the only one correct answer to this query, if you look at it, is just 01, because it's inside the ball. But in this approximation, in this mapping, there is 01, because it must be. It surely must be 01 because it's contractive, so it must be the same distance or closer than here. So it is. So it's just this. But at the same time, there is a new object here, 04, that was originally very far in the metric space, and this also happened quite easily, because from the point of view of the pivot P1 and P2, the objects 01 and 04 are almost the same, because it's 1, 2, 3, 4, 5, 6, 1, 2, 3, or 1, 2, half, and the same here and the same here. So they are kind of symmetric along this axis, right? In this particular Euclidean space, of course. But it reflects in that they are mapped almost to the same place. And this brings the error, and the error must be compensated. So that's why the LAESA method works in two phases. The first one is this mapping phase and filtering out everything that is outside of the ball. The ball is here, the square here. And then we cannot be sure with everything that's inside the ball. So we must refine, that's why query and refine strategy, we must refine the rest of the ball. So in case of, and this refining is done back in the original space. So we must compute the expansive distance, this one, to Q. So 01 Q and 04 Q, and we realize that 04 is outside. So this is basically LAESA, and here we see that the lower bounds are in the pivot space. The LAESA algorithm for range query could be performed really easily. Here we have the same situation, and this is the matrix that is visualized here. And we have the two phases, the sequential phase, the filter phase, and the refine phase. So in the filter phase, we just filter everything out which is outside of this ball. And we get these two candidates, and these are filtered out in the normal space. For the nearest neighbor query, it becomes a bit complicated, because we don't know the radius of the query. We just know the number of nearest neighbors we want to retrieve. And this could be done two ways. The first way is a one-phase algorithm that is basically the same as for AESA. I will show next slide. And the second is two-phase, because we can afford in the LAESA, we can afford the filter and refine phases. So here we have something similar. We can basically compute the query vector by the by the mapping to the pivot space, then sort all of the database objects with respect to the Lmax distance to the vector, to the query vector, and then we are going we are scanning the database in this order that we got here, and are computing basically the expensive distance and updating the candidate for nearest neighbors. And once the candidate becomes closer to the query than the Lmax distance, that is lower bound, then we are done, because we cannot find anything that is closer to Q, and we end. So this is how we can do that in LAESA. But we can use also the algorithm for AESA, and in AESA we cannot afford the the projection of the query to the pivot space, because we have so many pivots as are objects in the database. So just making the mapping of the query to the pivot space would result in exactly the same as what naive sequential serve would do for answering the whole query. So we cannot just compute all the distances that are possible in the database. So instead of the two phases, the mapping phase and filtering and the refine phase, we have just one phase. And but basically there are multiple phases, because it's just interleaving of these two. It's mapping to just one dimension, filtering, refining, then the second dimension, filtering, refining, and so on. So what it's done here is that instead of projecting the whole query vector, we project just the first dimension, sort the metrics just on again as in the previous algorithm, based on the Lmax distance to all the other distances that are stored in the matrix, and going in this ascending order to updating the candidate to the nearest neighbor. We can filter out something, because a few of them, of course, we can filter out. Then we get some reduced subset of the original database that was not filtered. So we do the same. So we do another projection, second dimension, and again resort that based on this one, filter and refine, and so on, until we end up with after a number of projections, we end up with with the nearest neighbor. And this was empirically proved to be done in a constant number of steps for AESA, but for the huge cost of indexing, because it's quadratic with the database size. So this was AESA. Now we come to hierarchical methods, the tree-based indexes, and there are many of them, because they basically built on successful designs of other indexing structures that go long to the history, to the 60s, 70s. We have B tree from 70s, then R tree from 80s. We have many different kinds of trees, and so they just borrow the properties from them and use that. So they are not completely new designs. They are just adopting basically tree structures already developed in the past. But what is interesting from the metric space case is that, of course, they must work with the hierarchy of metric regions as the boss, as I said, or the hyperplanes. Of course, they are recursive because they are tree structures, of course. And from the pivots point of view, they could use either local pivots. They use local pivots instead of the global pivots we saw in the pivot-based methods, where the pivots served basic as a coordinate system. Here, the pivots will work locally, because they basically are not pivots anymore, because they do not work globally, but they serve as the middleman for computing the lower bounds. So from this functionality, they are pivots. But they are local, just for one pivot is just for a fraction of objects in the index. They are also limited in lifetime. The pivots could be discarded or created, or not created, sampled from the data on demand. So the behavior and the life cycle of local pivots is completely different from the global pivots. The global pivots are just picked and they are forever. The local pivots are more dynamic and limited in their impact. Yeah. Of course, there are similar problems with tree-based methods as in other areas they came from. For example, R-tree, KD tree, and so on. The spatial indexes, spatial databases, because the trees are designed to decompose the space by some regions, and there often is the problem of overlapping sibling regions and huge volumes of the regions to cover all the data inside. So this is the same situation is in metric spaces. So these bad properties also were inherited from the original areas. There is also the problem of shape of the regions, because in metric spaces we have not much to choose from, because we have either the balls or the hyperplanes and nothing else, and combinations. So maybe we can construct rings out of balls. We can just take a large ring and subtract smaller ring, and we get large ball, subtract smaller ball, we get ring. But that's it. We don't have any other geometry, and we don't have any geometry at all, basically. All we have is basically the ball concept, but the ball concept is just an equation. It's not a ball. And the same the hyperplane. So we are kind of limited here, and we cannot just design various shapes like in spatial databases, because in spatial databases there is just Euclidean space, and you can use whatever shape of region you want: ellipsoid, box, ball, I don't know, stripe, something. Okay, first example of a tree used for indexing similarity or metric spaces is the GNAT, that is acronym for Generalized Near Neighbor Access Tree. And that this tree uses the principle of hyperplane partitioning. And here it's shown for 4 pivots. We see some node of the tree and how the database is organized. Basically, this could be a root of the tree, and there are some subtrees. And this root is organized such that the whole database is split into 4 subsets based on 4 pivots. We have pivots 03, 01, 04, 05. And the objects that are closer to 05 are one region, objects that are closer to 03 are this one, and so on. And we have here the hypothetical hyperplane, but just hypothetical. And now we have this query ball, and as I said when introducing the principles, if I want to test whether this region belonging to 05 overlaps the query, I will ask how far is the closest point in the query ball to 05, and this is the lower bound distance, blue one. And now the second question is, okay, I have this, or the second fact is, okay, I have this lower bound. Is there some upper bound from the other pivots that is larger? That is smaller than this lower bound. Okay, this one is not. Okay, the 03 upper bound is this one. It's the distance to the furthest object in the query ball from 03. From 01 is here. From 04 is here. And in this 04 we can see that is smaller than this blue one. So it basically says the closest possible objects from O5 is farther than the farthest possible objects from O4. So it says O5 is definitely out of the way because the query ball is shifted whole into the O4 region and maybe some others. So from this test, it follows that this region could be filtered out from search. And now we need to do this for all of the remaining regions. So computing lower bound distance from O3, comparing to this one. Of course, not this one. This is already filtered out. Comparing to this one and comparing and this one. And we will see that we can filter out maybe this O1, but maybe not, because this Euclidean visualization doesn't mean it's really non-overlapping in the term of the lower bounds and upper bounds, but it could be maybe. If we see like this one and this one, probably it will not be. Okay, and that's it. And then this query must proceed in the remaining O3, O1 and O4, and this one was filtered out. Of course, the tree was built recursively. I didn't say this construction was just for this level, and then recursively the same with the subsets and different pivots and so on. So we have four-way quaternary tree structure. There is an interesting fact about GNAT. Its co-author is Sergey Brin, which is co-founder of Google. In 1995, he introduced this GNAT, and 3 years later he founded Google. So he switched from metric indexing into search engines and making money. And so it's a really prestige company here in the designers of metric indexes. Okay, the second example I wanted to show is M-tree, which is versatile and highly cited and highly used metric tree that basically builds on R-tree, and the R-tree basically builds on B-tree. So this family of dynamic balanced page trees is basically sharing the common properties of building from bottom to top, from splitting nodes when they overfill and just growing to the root. So this is all the same. They are just different properties of where to insert entries and how to split, of course. But basically, when the M-tree is built, it's basically a hierarchy of nested balls. So this is what's really specific to M-tree. It's not nested minimum bounding boxes like in R-tree. It's nested balls. And once it's constructed, it's a normal hierarchy. And if we want to process this query, so we must proceed as usual from root to from root to leaves. So based on the overlaps of the balls, we will proceed to the branches that correspond to the balls. So in this case, OI, OP, and this OJ could be filtered from the search. There are many descendants of M-tree, like PM-tree, M-star tree, many others, because it's really a really simple tree that could be very easily extended. The third category is the metric indexes based on hashing structures, or hashing itself. And here it is, of course, different from traditional hashing. In traditional hashing of keys for just exact value, we wanted to have as randomized hashing function as possible to basically even the distribution and to basically ensure the same access cost for any key. Here we basically cannot be satisfied with just simple randomized function, because we must pose another property on the hashing function, and that is locality sensitivity, because it doesn't make sense to search for point queries in similarity search. The point queries have no meaning. Point query means that's a range query with zero radius, so it's point, it's just object. And basically in metric spaces we will hit nothing. So if we query by just point, it will miss everything, because that's why we define actually similarity, because we find not exact matches, point queries, but something that is closest. So we relax the matching condition to some extent, to some similarity. And that's why also the hashing function, if we want to do hashing for similarity search, must be locality sensitive. That means must provide some must preserve the property that if two objects in the metric space were close together, then also their hash codes must be close together, so they are locality sensitive. Otherwise we get complete noise. We cannot do nothing with it. So this is really strict condition that must be satisfied for similarity search using hashing. Once we have the hashing, everything else is just general design of hashing functions. We can have simple hash tables or hierarchical hash tables, and this is the case of D-index that I will just briefly mention. In D-index, that's hierarchical hash-based index that is based on so-called ball partitioning split functions, BPS, and this is really simple function. Consider this configuration. We have data in the database, data points, and then we have one function, and we have the hashing function that consists of pivot, that is O12 in this case, in this just example, then a parameter dm, this is this distance, and parameter raw, which is this distance. And based on these three parameters, we can hash all of the data using this hashing function into three values, 0, 1, and 2. And it will be 0 if the data point falls into this ball. So if data point is inside a ball with radius dm minus rho, then it's inside here. If the data is outside of this larger ball, so if it's outside of ball O12 dm plus rho, so it's outside, then it's 1. And if it's in the middle, here in this ring, then it's 2. And this is just ternary function that just produces three values for any object in the database. And we can easily define many of these functions based on different pivots, different dm, different raw for all of these objects, and concatenate the codes for the same data into not a bit string, because it's not two values, 0, 1, but it's three values, 0, 1, and 2. So, but we get this code based on this three value alphabet. And what does it mean? So we combine all of these. We can have many of these functions. And now, if the code for if a hashing code for an object has somewhere a 2, doesn't matter in which one particular of the functions, then it's pronounced, or then it's set to be in so-called exclusion set. And basically in here we see the situation for just two BPS functions. We have two rings, this one and this one, so we have two hashing functions, and we have concatenated two codes together into one larger. So in this case, objects that have no 2 in the all combined function, these objects basically are within these gray regions. So they didn't fall into any of the rings of the exclusion sets. And if object fell into at least one of the exclusion set, it basically belongs to the exclusion set, and therefore basically defines that the exclusion set is a union of the partial exclusion sets, so all of the rings. So in this case, we have the sausage, which is basically exclusion set, and then we have 3 buckets, A, B, C. We should have also D, but D is empty because the radii were not large enough to produce even inside here the D. So we have A, B, C. Look also that the C is the same as the C1 because it's the same criteria. It's like here and here it's the same. So here and here is the same. So it should not. It's not necessary to be connected, and still it's just one bucket. Okay, so this is the basic step, and now we can construct an hashing function out of this by initializing the first level, as in the previous slide. So we take all of the data objects, hash them. Some are hashed into A, B, C, and quite large part falls into X, so into the exclusion set. So then we take everything that fell into X and redistribute it again by different hashing functions, and again we get something else. We get A and B and something that again falls into X2. And again, we can redistribute another level, and so on and so on. So in this example, we have just 3 levels, and these 3 levels are basically chained like this. So we have all of the data in these gray buckets plus the exclusion set that is further solved here. So we have A and B, A and A2, B2 plus X that is solved here, and so on. So all of the data basically lies in this multi-level structure. Physically, it lies somewhere on disk. Of course, this is traditional organization of differently sized buckets of hash structures. What we got? Why this is good? Of course, we have locality sensitive function because that's how this is designed, because everything that is hashed here has the 0 and it's close together, so it's locality sensitive. Everything that is outside has 1, and again it's locality sensitive, because locality sensitive means it's not close to O12. It doesn't mean it must be close. It's also locality sensitive if it says it's similarly far from the pivot. So we get this and this locally sensitive, and this is something in between. So we have locally sensitive hashing, and we can basically solve queries. And it is especially, so queries, again, we have query bar here, and we just compute if it overlaps all of the buckets. If it overlaps, we go there. If it doesn't, we go no there, and so on. But what is especially beneficial for the index is that if we have really small queries that have the radius below row, so row, this is two row, and if we have queries with R that is below row, then we have really good position, because such a small query could be really quickly evaluated, because it could be the whole entire in some of the gray regions, and then it's enough to just access the bucket and it's done. Or it is in the wholly in the exclusion set here, then nothing is done in this level and it's immediately forwarded to the next level. So in this level we have again nothing to do, nothing more, just one operation. Or it's both, it's overlapping some of the gray regions and the exclusion set. Then it must be access one of the regions, like B, for example, and proceed here. So what we get for these queries, we are guaranteed that we are only accessing just one, at most one bucket, or at most one regions in this level, and possibly some at the other levels. So we will not exhaustively search the whole level, all of the buckets. And of course, because of the small radius, the query cannot span between or cannot overlap two of the gray regions. That's why we have introduced this kind of hashing. Basically, this is something like border area that basically splits or keeps the regions far from each other. That's why we have designed this. So that's basically the main reason. So the advantage, as I said, is really good performance for very small queries. The disadvantage is that the parameters raw and DM is difficult to search or to find because it could really disbalance the index. So this is basically disadvantage, and also it's also disadvantage that this the advantage of having very small query radius is basically not so cool, because these are really small queries. If raw is small, then the small queries are really small. So it's not so practical if raw is already small, and if raw is large. So this could be also applicable to larger queries. Then the exclusion set grows hugely. So in case of very huge exclusion set, there are too many levels here and too small regions here. So we deteriorate to sequential scan. So there must be some compromise about the size of the raw and the sizes of the queries. It's clearly beneficial in applications like near duplicate selection, for example, not near duplicate detection, or cell joins. In applications where we have really close instances of data that are basically duplicates, but are not really exact duplicates, but duplicates under the similarity constraint. So it means they basically fall into very small query. Then this structure is really a winner. Otherwise, it's not so cool. Okay, so this was hashing, and the other was hybrid access method. So many index structures combine multiple of these principles we have just introduced. I have two examples here, the PM tree and the M index. So in PM tree, basically the motivation for introduction of PM tree is to somehow reduce the volume of M tree region. And this is M tree region, this is just ball. And as you can see, there is just 4 or 5 objects within the ball, but the majority of the volume, okay, volume is again, doesn't exist in metric spaces, but something like volume is huge. So in this case, for example, we have a query that overlaps the metric region, the ball. So we must process this data region. So we must access the structure and so on. It's costly. But we will not find anything because there is nothing here. So this is a more general problem of so-called dead space. So if an index structure indexes subspace that is too large with respect to the data it contains, so there is too sparse data and too large region, then there is a huge problem of dead space. So in M tree there is a problem of dead space, and in PM tree it was reduced by reducing the volume of the ball region by further cutting out of some volume by additional information. And this additional information is global pivots. And from each global pivot, we can construct a ring that contains all of the data. And then we can basically think about the region as of intersection of all of these rings and the ball, and basically this is reduced overlap. And in this case, it is sufficient to test that this query, when this query does not overlap all of these rings and the ball, then it is disjunct. So in this case, this query does not overlap this ring belonging to P2, and therefore the whole region could be filtered out from search, because the query cannot contain anything from this because it's not overlapping. So this is basically the idea of PM tree. So taking normal M tree and just in second phase cut it out of the dead space. And in the bigger scale or view from the top, it looks like this. This is a hierarchy of FM tree, and this is the same hierarchy of the data and also of the regions, but furthermore cut off by rings. So we see that there is much less of the dead space here than here. Of course, there are some limitations. There are some pros and cons, because there is some overhead, because there is the new pivots introduced, but in overall PM tree can reduce the search cost. And the second example is M-index, that basically is quite really rich indexing structure, because it combines basically all of the principles ever used in metric indexing. It uses principles from pivot tables, hyperplane partitioning, ball partitioning, hashing, and also very, very old techniques like B+tree, because everything what is done based on these metric basically indexing is then transferred into linear case that are indexed in B+tree. So it's basically mapping from M-index from metric space into B+tree. The basic part of M-index is so-called I-distance, which is some older method. It was introduced for spatial databases, and it's basically mapping from multi-dimensional or metric space into one-dimensional space. So one-dimensional space is just a real line, and what it does is that it assumes a number of clusters like here. So we have clusters of data, C0, C1, C2, and each cluster consists of some objects, has its center in a pivot or in some object, and we now construct for every key, for every object in every cluster, one value that is then marked in this real line, and it's composed of two components. The first component is the just ordinal number of the cluster. So it's just 0 for cluster 0, is 1 for cluster 1, it's 2 for cluster 2. And then it's the real part of the number, and that's basically the proportion of this basically normalized distance from the center to the border. So let's say we have this object that is from this distance here, and this object in their distance here, and we have C0 cluster. So we have the interval between 0 and 1. Basically, C could be any number, but it could be basically just 1. So let's suppose C is 1. So we have 0, 1, 2, 3. So for C0, we have everything mapped in this interval 1 and 0 and 1. And within the interval, these two objects are basically here. This object and this object is farther from P, so it's farther also on the real line, and so everything is mapped here. From the second, or from the C1, it is in the other bucket, or in the other interval between 1 and 2, and again the same. This distance means it's here, this distance it means it's here, and for the third, and so on. So we got mapping from a number of clusters into a real line. And then if we want to query this data by a normal query, so we got queryable here, then it's sufficient to map the queryable into intervals on the real line. And it's again very simple. We just compute the intervals that we need. How many intervals? It's so many intervals that there are overlaps of those clusters with the queryable. So we have two clusters, C0 and C1. So there will be two interval queries. And the intervals are defined the same as were the keys for the objects. So it is basically from this distance, because I have distance Q to P minus R, I get this distance, so it means it goes here. The maximum is here, and I have the same for C1, and I have nothing for C2 because it's not overlapping. So once I find all of the keys here based on these two intervals, I get basically everything is inside this queryable and these two clusters. So this is I distance. And the M index builds on this simple idea even further. It splits the space. It's already partitioned into the clusters, but it moreover splits the space into by the way as GNAT does. So it's the hyperplane partitioning by multiple pivots, and these pivots, and that's the trick, is the same pivots as were these used for the clusters. So they are reused. So there is much of reuse in M index, and there are other additional tricks that even more reuse other information and even more split the space or partition the space in even more refined partitions. We see that we have some very rough partitioning here into three balls. Here is moreover overlap with this hyperplane based partitioning, so we get more of these regions. Then we get even more by splitting by hyperplanes, reusing the other pivots, and so on. So we get with the same information, many just fragmented representation of the space. And the final key that is used, the same as I distance here, is then computed like this. So it's basically again I distance, but with the other identification. So that there is not just three regions like here, but there is many more of them here. But otherwise, within the region, the real part is again the distance. So this is M index. There's also some information like from M3, remembering the distances between the centroid and the data and so on. So it's really hybrid structure. Okay, so this was just short overview of indexes, metric indexes, and now we do the last part, and then that's performance measures. So we are really concerned by performance because this whole problem is about performance. It's about efficiency, and the performance, of course, matters when indexing and querying. So these two must be solved together, because if it's too expensive indexing, then it doesn't pay off with the querying. So we must really take this as a combination. And there is another question of cost measure. What to measure? What cost to measure? So we have logical types of costs. So for example, everything that I just presented was primarily optimized. These metric indexes are primarily optimized to minimize the number of distance computations, because it's expected that the most expensive, computationally expensive part of this search process is the time spent within computations of individual distances, the delta distances. So that's why minimization of these distance computations leads to overall speed up. But this could not be always true, because there are some distances that are very cheap, like Euclidean distance. So there also come other logical costs into play, like I/O costs, so disk access costs, so storing and fetching data from disk from secondary memory. Then there are also internal costs, as I said. There are some task-specific internal data structure algorithms that are somehow complex. It depends on the algorithm, because task-specific. And there are many others, like networking, synchronization of parallel processes. There are many other logical costs that could be taken into account. And of course, what's finally the real thing when running these algorithms in some applications, some systems, is the real time, is the physical real time, so wall clock time, so the response time when the user really issues a query and how fast in real time the user gets the answer. Okay, so now for the logic cost. So as I and of course before I proceed to the logic cost, we must discuss what to optimize, because as I said, we must take together the indexing and querying phase together, because we optimize the total cost of indexing and querying. Why? So imagine we have just sequential scan, so that we have no indexing. We just have the database, and we directly do the query. And the query means I take the query object and compute distance to all of the objects in the database. So it's just linear with the size of the database. This method, it's baseline method. It doesn't require any indexing, and it's a sequential scan. But and it also has no assumption on future queries. It's just sequential scan without any other context information. But in databases, we basically assume that we invest some time for indexing database. So this takes some resources, time, real time. But this real time will be paid by, or amortized by, reduced query costs. So we expect that for indexing, the offline phase, the indexing, we get for the price of indexing, we get reward of very cheap queries. That's basically the database expectation or the basically assumption of any indexing. Indexing means index is built because of cheap queries, and altogether it pays off. If it doesn't pay off, then it makes no sense. If we know that we will ask this particular database just one time and then we throw it away, then the sequential scan is the best way we can do, because in total it will be cheaper than very expensive indexing and very cheap querying, because there will be just one query. But in most cases, we expect there will be one indexing that is expensive, but really many queries that will basically make the indexing worth the effort. So this is the database scenario. Of course, this is not valid in all situations. We could have streaming databases. We could have really basically databases that are not supposed to be queried, but are like archives. Or we just put outdated information there. So there is lots of updates. There would be a lot of indexing and no queries. In that case, doesn't pay off. So indexing is only useful when there will be a huge load of queries after the indexing. Okay, so this is very important preliminary. And now we must also select such, when designing a index structure, we must select the measure, the cost measure, that basically is appropriate for the expected situation in real processing. So for example, if we expect that the problem that we will solve will be in Euclidean space, we just cannot assume we will have expensive distance measures, so we cannot use number of distance computations as the ultimate measure for measuring different access methods, different indexes, because number of distance computation is not the main part of the real time. But if we have application that there really is expensive distance metric, like quadratic for distance, for example, then it's enough to have the optimization or the evaluation criteria based on number of distance computations, because then it really happens that the real time will be spent mostly in computing the distance. But otherwise, we must be careful about this. If we have cheap distance function, we must resort to another. Basically, in basic terms, we must resort to a subset of logical cost measures that are guaranteed to be dominant in the real time, in the expected real time. So this is basic guideline. Okay, so the first one is the distance computation, number of distance computations, DC. So if this is dominating component in the real time, then we use it. And when it's dominating, it's mostly dominating if we have really expensive distance functions. So expensive means superlinear with the size of the descriptor. Now the end is the size of the descriptor. Or we have at least really large descriptor. If you have 1 million dimensional vector, it's really large. So also computation of distance between two 1 million dimensional vectors will be expensive, even for distances that are not quadratic but also only linear, because we have large objects. So this is first hint when to use or when to expect it will dominate the real time. And the second hint is that there will be the I/O cost will be out of the question, because we have so small database that it fits the main memory. So nowadays we have large memories. We can have 40, 64 gigabytes of memory, no problem. And if this and if the database fits the main memory, then there is no disk access. And then and in case that disk access would be the dominant cost, now it's no in the question. And the second most dominant cost could be the distance computation. So if it's the case, it could be again used as the default logical measure for performance. So this is distance computation. The second is the disk accesses or I/O costs. Basically, this is the second most important criteria when evaluating the performance of indexes. Basically, this is the classic database-oriented type of cost. It could also be measured in transactions per second, but this is more in the benchmark phase that we are comparing the products. And here there are many important issues that needs to be taken into account. First, the technology. Most of the algorithms, data structures designed for databases are still optimized for HDDs, for magnetic drive technology. And this is just relic of time, because HDDs were here for decades. But it changes nowadays. Nowadays the SSDs are basically taking over HDDs and are becoming not only as the fast storage systems for operating system, but also become primary storage system for databases, not just for software, not just for application, but for databases. That's the first factor. And then there is also time factor. The database, the HDD technology really changed in decades. So For example, in 1990, there was this kind of situation. It's for real hard drive. It was for Seagate with 20 megabytes of capacity, which is funny nowadays, but it was really a huge hard drive that time. And the properties of that old disk, oh, of course the consumer disk, it's not nothing high end, it's low end disk, and it was seek time was 65 milliseconds and transfer time was something like 600 kilobytes per second. Transfer means reading here. And now let's try it for our running for some example, just statistical example. Let's have some metric index, or doesn't matter if it's metric index, we have some index that is 100 megabytes, and we have organized these 100 megabytes on the disk and in 4 kilobyte disk pages. So we have something like 25,000 disk pages, and of course we can access these pages randomly by random access or continuously. So we have these two ways of access to data, by random access or continuous access. This is something similar we already had in the implementation of the top K operator by the Fagin and threshold algorithm. We have there the parallel scan and then the random access. It's something similar here and has the same consequences. Random access is of course more expensive because of the jumping of the technology that is needed to randomly access something. So let's get back to our 1990 example. So we have this index, and then using this hard drive with these parameters, sequential scan of the whole 100 megabyte index. Of course, there is just 20 megabytes capacity, so it will not fit there, but let's imagine it's 100 capacity. These 100 pages, when read sequentially, so with just one seek and then continuous read, would need 167 seconds, right? Because it's 100 megabytes, 60 kilobytes per second, it's 167 seconds. If we use, instead of sequential scan, a hierarchical index that only needs to read 1% of pages, but not continuously, but randomly, we would need, by this random access, 1%, so it means 256 pages and also 256 seeks to that random pages. That means we spent 16.5 seconds for seeking plus 1.5 seconds for reading. So we get 18.2 seconds. So when compared to the sequential scan, we get something like 10 times speed up. So it's cool. And that's why also, that's the reason why the hierarchical indexes in 70s basically were developed and really worked in database systems, because they really are faster on this technology. But what happened in 30 years later, we have completely different statistics. We have some 6 milliseconds of seek time, which is 10 times better. But we have 100 megabytes per second transfer time, which is 2 orders of magnitudes better almost. And what happened? Why this is so different? Well, it's not so difficult, because there are some factors that are limited by physical laws, like the seek time and latency means there is a head in the magnetic drive that must move, and of course there are physical limitations. There are mechanical, kinetic, energy, blah blah blah, these kind of things. So the improvement in these mechanical characteristics are not so heavy as in this transfer time. And why this transfer time is so improved is because of the Moore law, because the transfer time doesn't relate to physical movements in the disk, but to the density of information stored in in the magnetic plates. And then there, the density of the information follows the Moore's law. That's basically much more flexible than the physical laws. They are basically rigid, but the Moore's law allows to double not only speed of processors, but also the capacity of information media, of digital media. So that's why we get basically completely disproportion between these two numbers and these two numbers. So now the situation dramatically changed. So the same example, sequential scan of 100 megabyte index, 100 pages continuously, we get 1 second because it's the read time, right? It's transfer time, we have 1 second. But if we use a tree index that only searches 1% of the pages, but by random access, so only the random access takes 1.5 seconds, and plus completely negligible search time, so we get 1.5 seconds of read using index that basically spared 99% of pages for reading, but we get slowed down by 66%. So what's the problem? Yeah, the problem is in this proportion and completely different situation to this proportion. And that's also why in the last decades the management of data switched from using hierarchical indexes that require random access to basically sequential scan. It was much easier, cheaper and everything, and faster. So it basically was some judgment on the hierarchical MAMs or hierarchical indexes that they will not survive because of this. They are slower. They look faster. They basically are slower. Okay, so they are almost dead in 2020 or 2010 basically. But in the meantime, the solid state drives came and the situation completely changed. First, the sequential read got to speeds like this, so it's order of magnitude faster than the modern hard drives, but there is no seek time now, so there is nothing like this bottleneck. So quite low end SSD can basically read 300,000 of disk pages per second, and this is parameter or this is evaluation that was reported. This is not just a thing just computed here. So we get to completely different situation. The landscape again changed. So now with SSDs, we get the sequential scan of the same index for 45 milliseconds. But when using index that again uses random accesses and reads only 1% of the pages, then we get only to 0.85 milliseconds, basically 850 nanoseconds, which is basically 50 times speed up to the sequential scan, which is basically even better than it was in the 90s. It was just 10 times. And here it's 52 times. And theoretically, of course, 100 times is the best because it's 100 reduction of the pages. It's 99%, right? So with SSDs, we get to completely new era where the indexes that are doing random access basically are resurrected, and basically the history repeats, because now we are in the same situation as the indexing technology was in 70s basically. So it is extremely important to consider the hardware platform when measuring I/O costs, so disk accesses. First, it's really important to have the model of the device, if it's HDD, if it's SSD, and what are the parameters, because based on this we can get to something that is completely negligible. So for example, on SSD, it might turn out that the computation of the distances is much more contributing to the real time, because the access is so cheap that it's basically negligible. So it's really interconnected, and it must be weight if the real time is composed of I/O costs or distance computations or something else. So there is no clear choice. Everything must be considered. So this is I/O cost. The third is internal cost, and this is related to the basically specific behavior of the algorithm that we are inspecting or comparing in different structures, different indexes. And I have two examples here. First is incremental KNN processing. This is the Hjaltason and Samet's algorithm for implementation of the incremental k nearest neighbor search. Incremental k nearest neighbor search is basically interactive k nearest neighbor search, where the user wants to retrieve k nearest neighbors, but after the user gets the results, he may decide he wants more. So this is exactly the same as Google provides. So Google gives us 10 results on the first page, but offers us, do you want another page? So next page, next 10, next 10, next 10, and so on. So it's incrementally, it brings some interactivity with the user. An incremental algorithm for KNN basically implements this. So it computes the first k nearest neighbors, returns to the user, keeps the state of the algorithm in memory, and then when it gets feedback that the user wants more, then it proceeds and gets more, and again returns it and waits and so on. But for this keeping of the result in the memory, there is some extra structure, that there is a heap of requests maintained in memory that basically contains everything that the algorithm can continue with the KNN. Basically, it's not done, but it's in progress. And basically, this heap of requests is by design. It could basically expand to the size of the database. So it could be really huge auxiliary structure, that is the helping structure, that basically could really be a problem for the measuring of the performance, because it is optimal in distance computations. Basically, it's equivalent for range query. So basically, it's the really cheapest way how to answer the range query. But in other costs than distance computations, it's really there is a huge overhead. So, as I said, the heap of requests could be extreme. So this is one example. The other example is pivot tables. In pivot tables, there is the distance matrix scanned based on different criteria. In AESA, for example, or LAESA, we can just sort based on one dimension, then filter and refine, then project another dimension, filter and refine, and so on. So there is huge overhead just scanning the matrix, And in terms of distance computations, again, it's optimal. But in terms of the other operations like scanning the matrix, this is completely ignored. But of course, this will reflect in the internal cost. So, for example, consider 100 to 28 dimensional vector dataset. So dataset and some LP distance, like Euclidean distance, and we want to index this dataset by pivot tables that have, to be easy, 128 pivots. So it's basically the same dimensional dataset, but in this case, the dimensionality is in the pivot space. So what we do a transformation from 128 dimensional vector set into another 128 dimensional vector set, and we have the matrix. And then we basically scan the matrix. And even mapping the query vector the query object into query vector using these 128 pivots is the same complex as evaluating the problem in the original space by sequential scan. So in this case, for this case, the 228 pivots and pivot table is really not a good choice, because it can only bring overhead and no speed up at all. So, and it's all because of the internal cost, so we must be careful of what's happening inside the query, inside the indexment query. And the last slide I want to show here is the ultimate cost, and it's real time. Of course, real time is the ultimate cost that then is the right one, or that's the one that really matters, because we must wait for something. But it's really tricky to prepare conditions for comparing different structures, different algorithms based on real time, because then there are many factors that affect real time. It's not only the algorithms, but it's the hardware platform, software system platform, other processes running. It's the language that one method was implemented, the other was in another language, maybe. The compilation mode, one is in debug mode, one is release mode, there are optimization or not. There is other code optimization that is the programmer responsible for, and there are many external factors that basically do not relate to the core of the algorithm, but they affect altogether the real time. So that's why it's not recommended to use for comparison of methods on the logical level. For example, I don't know if bubble sort is better than quick sort or something. That, well, in this case it's obvious because there are different complexities, but if I don't know, something else. So that's why we use the logical cost measures. The real time is used in the final phase of testing software, like in benchmarks. If we have two products that should be optimized and should be the most optimized and most effective in the implementation, then it's easier to compare them, and that's what's happening. So if I have two database systems, I have Oracle's database system and Microsoft SQL Server or something, I can measure their performance because they are two matured products, and I can measure transactions per second of one and the other, and then it's clear number. It's nothing logical. It's really physical. But what we have discussed today is not products. It's just algorithms, and in this case, it's really tricky. So, but still, it's really hard to choose the right performance measure. For example, I have two results here. For example, consider a real-world example of a database of peptides, 5.5 million of peptides. These are just pieces of proteins, and these peptides were just modeled by 32-dimensional vectors, and some very cheap variant of Hausdorff distance, just linear variant of Hausdorff distance, was used for the similarity for the distance. It's basically like Euclidean distance, so it's a really cheap distance. And this is the cheap distance is something that suggests, okay, we should not compare different methods for this data set based on distance computations, because it's cheap distance. And there are surely other components of the complexity that are dominant. And we show that it's true. If we compare the methods M3 and pivot tables that are indexing this database by the proportion to the sequential scan, but in the terms of distance computations needed to answer the query, we get to these nice numbers, right? So we get M3, and the parameter here will be the database size. So from smaller, from 1 million to the 5.5 million. So for M3 we get nice behavior starting for 25% so it's already 4 times faster than sequential scan here, and goes to, I don't know, 14%. So M3 is 14% here in this measurement, in the logical measurement of distance computation. It's 40% of the sequential scan. Pivot tables is even better. It's 20 times faster than sequential scan for all of the sizes of the databases in the logical performance units. But what happens if we measure the real time? Here it aggregates not only the computation of the distances, but also access costs, so IOs, and the internal costs, as we have discussed. And here the situation is dramatically different. So for the same queries and the real time, we get completely different behavior. We have here also the sequential scan, which is this middle line. So this is sequential scan, naive sequential scan, no indexing at all, nothing. And here we have the winner here. This is the pivot tables, but here it's, for the small databases, it's still very good. But here, after 2.5 million, it begins to be extremely slow and even worse than the sequential scan here. And this is because the effect of the internal costs that are exceeding limits took place. So here the distance matrix is enlarged because of growing database here, so much that probably the system must swap the data to the virtual memory or something, and it really hugely increases the cost. On the other hand, the M3 that was here the worse than the pivot tables is now the clear winner in real time, because it not only is optimized for reducing the distance computations like here, but because it's tree structure that does not scan a whole matrix like pivot tables, it's also optimized for I/O costs, and that's because and that's the reason why it really keeps very good numbers here, and only gets to, I don't know, 1% or no, it's 1 second of the search. So it's still, comparing to 5 seconds of the sequential scan, it's basically 5 times faster, and the pivot tables that should be the fastest are basically 2 times slower than sequential scan and 10 times slower than M3. So this is only to demonstrate that it's really tricky to just take one value and take it as a valid and universal result. So this was the last point of this talk, and that's it.